Very good morning to all of you. From today, we are going to start studying about pulse code modulation and related systems, which also includes delta modulation. The pulse modulation systems are not completely digital, as the amplitude or width or position of the pulse transmitted may vary continuously in accordance with some message signal. Pulse amplitude modulation is the simplest pulse modulation system. But for this reason, the PAM signal is used to get a complete digital. Uh, a very good morning to all of you. From today, we are going to start studying about pulse code modulation and related code modulation systems like delta modulation. As we know, the pulse modulation systems are not completely digital, as the amplitude, width, or position of the pulses transmitted may vary continuously in accordance with the message signal. Pulse amplitude modulation is the simplest pulse modulation scheme. And for this reason, the pulse amplitude modulation signal is used to get a complete digital system. The PM signal is a discrete time signal, where signal on time axis is discrete and the amplitude axis it is continuous. To get a digital signal from this signal, the signal on amplitude axis should also be made discrete. To achieve this, the PAM signal is quantized, and quantization allows us to take on only finite values. We make it discrete on the amplitude axis, on the x-axis, although the resulted signal has digital values, making it discrete on the amplitude axis and then coding it on the y-axis makes it completely digital. So why do we need to convert an analog signal into digital? Because a digital signal is superior to an analog signal because it is more robust to noise and can easily be recovered, corrected, and amplified. For this reason, the tendency today is to change an analog signal to digital data. Most of the analog systems, have now been replaced by digital equivalents. In this section, we describe two techniques, pulse code modulation and delta modulation. So topics discussed in this particular lecture uh, includes PCM and DM and also noises associated with them. So what are the steps in PCM? PCM consists primarily of three steps and which involves digitization of an analog signal. The first step, all you know, is sampling. Second step is quantization. And the third step is binary encoding. After the third step, the digitally encoded signal comes out. So before we sample, we have to filter the signal because we want to limit the maximum frequency of the signal as it affects the sampling rate. All of you are aware with the Nyquist criteria. So filtering should ensure that we do not distort the signal, that is remove high frequency components that affect the signal shape. Now these are the components of a typical PCM encoder. This is the analog signal, continuous in nature. PCM encoder first samples it and discretizes it on the x-axis. Then comes the process of quantization, which starts discretizing the y-axis also. And after the quantization, the quantized values are encoded in a serial bit of 1 and 0, serial bit series of 1 and 0. So sampling, quantization, and encoding, all them put together make a pulse code modulation system or pulse code modulation encoder. Now let's talk about sampling. That analog signal is sampled every t seconds, t subscript s second, where t subscript s is referred to as the sampling interval and its reciprocal is the sampling rate or sampling frequency. There are three sampling methods. One is the ideal sampling method, where an impulse at each sampling instant is provided to sample the y-axis value of the analog signal. Then there is natural sampling. It's not an impulse, it's a pulse with samples. It's a pulse of short width with varying amplitude. Again, there is flat top sample, which is a sample and hold circuit like natural but with single amplitude value. This process is referred to as pulse amplitude modulation, and the outcome is a signal with analog values. However, it is non-integral values. So if you sample any message signal like this, as you can see on your screen, what you are going to get a non-integral value, which is not yet digital, but it is discrete in the time axis. So an analog signal is sampled at different instants of time, at discrete instants of time, and this has been indicated on in this diagram using this magenta marker. There are three types of sampling that we have discussed: ideal sampling approach, natural sampling approach, which also takes into account the slope of the y-axis of the signal, and there is a flat top sampling which uh, thresholds the particular sampled signal onto a flat value. According to the Nyquist theorem, the sampling rate must be at least two times the highest frequency contained in the signal. So all of you are aware with this requirement, and here you can see the difference between a low pass signal where there is a maximum frequency component f max, and there is a band pass signal which is contained in the frequency band between some f min and some f max. Nyquist rate for both the cases is 2 into f max. So whether it is a low pass signal or band pass signal, the maximum frequency component has to be multiplied by 2. For an intuitive example of the Nyquist theorem, let us sample a simple sine wave at three sampling rates, like fs equal to 4f, this is 2 times the Nyquist rate, fs equal to 2f, this is exactly equal to the Nyquist rate, and fs sampling frequency equal to f, which is one half the Nyquist rate. So one is called oversampling, which is the case when we are sampling more than the Nyquist rate. Then there is Nyquist rate sampling, ideal sampling, and another is one half the Nyquist rate, which is undersampling. So figure that will follow, which show the sampling and subsequent recovery of the signal, and it can be seen from the figure that follows just after that slide that sampling at the Nyquist rate can create a good approximation of the original sine wave. Oversampling, which is represented in part B of the figure, can also create the same approximation, but it is redundant and unnecessary because to generate the samples at designated time instant, we need a complex circuitry and computational load is also there. So sampling below the Nyquist rate produces some kind of an error because it does not produce a signal that looks like the original sine wave. Just have a look at it. The A figure number A, where there is Nyquist rate sampling at twice the maximum frequency rate, and we can approximate the original signal to some extent. Just like the sinusoidal wave, the rounded off edges have become now more sharp and it looks more like a triangular waveform. However, the magnitude characteristics have been preserved. Oversampling also preserves the magnitude characteristics, and however, undersampling may result in serious distortion of the even the magnitude of the signal, and how it looks like, and in between values are not recovered. If you want to recover the original signal, most of the samples would be distorted if we do undersampling. Telephone companies digitize voice by assuming a maximum frequency of 4000 Hz. Just to give you an idea, what is the maximum frequency component in real world signals of interest? The sampling rate therefore is 8000 samples per second. A complex low pass signal has a bandwidth of 200 kilohertz. If I ask you what is the minimum sampling rate for this signal, now we are talking about the bandwidth. And if you recall the figure that I have just shown you, the bandwidth of a low pass signal is between 0 and f, where f is the maximum frequency in the signal. Therefore, we can sample the signal as 2 times the highest frequency, which is 200 kilohertz. The sampling rate is therefore 400,000 samples per second. Now we come to quantization, which is an essential process in digitization. Sampling results in a series of pulses of varying amplitude values ranging between two limits, a minimum value and a maximum value. The amplitude values are infinite between the two limits because we can take on any value and we can generate any number of samples. We need to map the infinite amplitude values onto a finite set of known values. This is achieved by dividing the distance between the mixing line into some number of zones, each of a particular height, and let me call this height as delta. So delta is equal to the difference between maximum and minimum, which is the signal excursion, divided by the number of zones. That will give you the delta, and this delta, the midpoint of each zone, is assigned a value from 0 to L minus 1, resulting in L values. Each sample falls in a zone in then approximated to the value of the midpoint. So if a sample lies above the midpoint, it will be taken down to the midpoint, and if a another sample lies below the midpoint, it will be there will be some addition in that the value of that signal, and it will be taken up to the midpoint. However, every sample falling in that zone is approximated to the value of the midpoint. So that is called quantization. We are just truncating all the possibilities onto a finite set. Quantization zones. Assume we have a voltage signal with amplitude Vmin and Vmax. There is an excursion between minus 20 volt and plus 20 volt. We want to use 8 quantization levels. So capital L is equal to 8. How are we going to determine the zone width? Zone width is given by the excursion of the signal between min and max value. So 20 minus 20 upon 8, that gives you 5. So zone width is 5. So 8 zones are minus 20 to minus 15, because we have zone width delta is equal to 5. So we will try to truncate everything between these values. So 5 is the number after which another zone starts. So minus 20 to minus 15 is the first zone, minus 15 to minus 10 is the second zone, minus 10 to minus 5 is the third zone, and so on. The midpoints of this zone are minus 17.5, minus 12.5, minus 7.5, and so on. So we have now defined the zones and their midpoints. Any sample lying in that particular zone, say if a sample lies between minus 15 to minus 20, if I say the magnitude of that sample is minus 16.5, then I will consider that it lies in zone number 1, whose midpoint is at minus 17.5. So instead of calling that sample minus 16.5, I will call it minus 17.5, because it has been mapped to the midpoint value. Now the last step remains, which is to, after quantization, assign codes to the zones. Each zone is then assigned a binary code. The number of bits required to encode the zones, or the number of bits per sample, as it is commonly referred to, is designated as follows. NB is equal to log base 2 capital L. So our example, NB is equal to 3. The 8 zone or level codes are therefore 0000001 010 011 100 101 110 and 111. Assigning codes to the zone 000 will refer to zone minus 20 to minus 15, and 001 to minus 15 to minus 10, and so on. So it's pretty simple how we assign codes to individual zones. We can represent this graphically for better understanding, and we have this normalized amplitude on the y-axis and time on the x-axis. Samples generated have been indicated using magenta impulses and markers, and the quantization levels you can see here. The midpoints have been defined. From 0 to t there is one quantization level, from t to 2 there is another quantization level, and so on. These quantization codes have been generated considering their midpoint of these individual zones, and you can see at the bottom of the slide the quantization code 2, the encoded word is 010. For quantization code 5, the encoded word is 101, and for quantization code 7, the encoded value is 111, and so on. There is also a normalized value of error, which is the error when we round off a particular sample to the midpoint of that zone. So if we round off a particular value, say 7.5, to the midpoint between D and 2D, then what is the quantization? What is the total error occurred? So these errors have been indicated on the x-axis just below this graph. When a signal is quantized, we introduce an error. As I have just discussed, the coded signal is an approximation of the actual amplitude value, because suppose a particular sample lies above the midpoint of that zone, and its value needs to be reduced to map it to that midpoint. And if it lies below the midpoint, its value needs to be increased in order to map it to the midpoint. So there is an error in the positive or negative direction when we do quantization. So the difference between the actual and coded value or midpoint is referred to as quantization error. The more number of zones, the smaller will be the width of the quantization level. Delta will be smaller, which results in smaller error. But the more zone, the more bits required to encode the samples. Therefore, higher will be the bit rate, and it is computationally and more in terms of hardware also expensive to increase the bit rate. Higher bit rate means better performance, however, at a cost. So signals with lower amplitude values will suffer more quantization error as the error range delta by 2 is fixed for all signal levels. That's the maximum error range. Non-linear quantization is used to elevate this problem. Goal to keep the SNR signal to noise ratio fixed for all sample values. So the approach there are two approaches for doing this. The quantization levels follow a logarithmic curve, smaller deltas at lower amplitudes and larger deltas at high amplitude. And the another solution is compounding. The sample values are compressed at the center into logarithmic zones and then expanded at the receiver, and the zones are fixed in height. So compounding is a very effective technique, and we frequently use this technique for reducing the quantization error. So there is also some issues with the bitrate and bandwidth requirement of PCM. The bitrate of a PCM signal can be calculated from the number of bits per sample into the sampling rate. So if the number of bit per sample is NB and sampling rate is Fs, it is the bit rate is NB into Fs. Uh, the bandwidth required to transmit this signal depends on the type of encoding, line encoding that we have used. And we have referred to the previous section for discussion and formulas. We have in the previous lecture also discussed some bits about this particular topic. A digitized signal will always need more bandwidth than the original analog signal. So this is the price we pay for our robustness and other features, uh, noiseless behavior of digital transmission. We want to digitize human voice. If I ask you what is the bit rate assuming 8 bits per sample, so we should know what the human voice, how much frequencies, how many frequencies contains it contains. It contains frequencies from range 0 to 4000 hertz. So sampling rate and bit rate are calculated as follows. Simply the sampling rate according to Nyquist is 8000 samples per second, and that's the bit rate comes out to be uh, 8 into 8000, which is 64 kbps. So if you want to digitize the human voice, this should be the bit rate. Now let's talk something about the decoder. We have talked much about the encoder. Now it's time to talk about the PCM decoder. So it receives an analog signal from a digitized signal. We need to reconstruct that original analog signal. So we use a hold circuit that holds the amplitude value of a pulse till the next pulse arrives. We pass this signal through a low pass filter with a cutoff frequency that is equal to the highest frequency in the pre-sampled signal. The higher the value of the L, number of quantization zones, the less distorted a signal is recovered, and that is understandable. So this is a component of a PCM decoder, that is a hold circuit which receives the digital data, and the amplitude values of the pulse is held till the next pulse arrives, and that's how it differentiates between a high and a low amplitude, and this value is then low pass filtered to recover the original analog signal to some extent. We have a low pass analog signal of 4 kilohertz. If we send the analog signal, we need a channel with a minimum bandwidth of 4 kilohertz. If we digitize the signal and set 8 bits per sample, we need a channel with a minimum bandwidth of 8 into 4 kilohertz. So that you can see from your own eyes that 32 kilohertz is required for the digitized signal. However, we can send the analog signal with 4 kilohertz, so more bandwidth is required. However, the promise associated with sending a digitized signal is much more than the compromise on bandwidth. Now let's talk about delta modulation. This scheme is a variant of pulse code modulation, and this sends only the difference between pulses. If the pulse at time say tn plus 1 is higher in amplitude value than the pulse at time tn, then a single bit say 1 is used to indicate the positive value. If the pulse is lower in value, resulting in a negative value, a 0 is used. So this sends you the difference between the pulses and not the individual pulses themselves. This scheme works well for small changes in signal values between samples. If changes in amplitude are large, this will result in large errors. Okay, so the process of delta modulation is like this. So you have a continuous signal, and the difference is approximated using a staircase function, and generated binary data is in terms of 0 and 1, and the amplitude is indicated on the y-axis and time on the x-axis. The components of our delta modulator is a comparator and a delay unit and the staircase maker, that staircase function that we have seen here, that is generated using a staircase maker. Now, by a delta modulation technique, uh, we what we usually do that a pulse generator produces a pulse stream of positive pulses. First of all, the modulator receives the pulses and the output of the difference amplifier, which is the nothing but comparator here in this picture, and the modulator output is the input pulse train depending upon the polarity of that modulator. If the output is a positive pulse, if the input is positive, it's a negative pulse. If the input is negative, the magnitude of delta t, which is the difference between the approximation and the original message, plays a very important role. And according to probability theory, the probability of this difference being exactly zero is zero, and hence delta t, which is the difference, I am calling delta t as the difference between the message signal and its approximation, its probability of being zero is zero, and it is always either positive or negative. When the output of the modulator arrives, it is applied to an integrator, and the input signal, which is the original message signal empty, and the integrator output are compared in a difference amplifier whose output is delta t. Okay. Now, there's another variant of delta modulation. Before we go to DPCM, I would again like to talk about the requirement of the behavior of the staircase function. This approximating waveform, which is the staircase function, which I am calling m cap t, uh, I let, for the sake of convenience, call it m cap t, and this message signal denoted in this magenta line, this analog signal, let's call it mt. This m cap t needs to closely follow mt, and only then the record waveform resembles. And there is a situation at the top of this figure, say the top of at the peak of this magenta analog waveform, you see that the waveform is unable to follow the original signal mt. Staircase is unable to follow it because the slope of mt is greater than the slope of m cap t. So this is called uh, this is an error. This is a slope overload error, and this needs to be avoided. And what we can do for avoiding this slope overload, and there are two types of slope overload: a positive slope overload and a negative slope overload. In situations when the slope does not matches between the mt and n cap t, the slope overload error occurs. It occurs when the message signal is very slowly varying, or this staircase signal varies very fast. So both these situations need to be avoided. Now, instead of using one bit to indicate positive and negative differences, we can use more bits and greater quantization of the difference. Each bit code is used to represent the value of the difference, and the more bits, the more levels, the higher the accuracy, and that is understandable. Now, a very important part here is noise in PCM systems. The noise performance of PCM systems and related systems needs to be quantified, and we need to learn about what is the common quantization noise introduced when we use these systems. So, noise in PCM system is of two types mainly. One is transmission noise introduced outside the transmitter. We are not talking about that. Another is quantization noise introduced in the transmitter itself. We are talking about this only. So quantization noise in case of PCM system, a typical pulse code modulation system, is denoted by NQ, and its value is S square upon 12. So we should know and learn what this value is for different types of PCM systems and in which condition. So for a typical PCM system, if the message signal is there and there are say equal voltage intervals, each having a magnitude of s volt, So this S is the magnitude of voltage interval. The quantization noise is given by S square by 12. This particular value can be derived, and we will derive it in a later lecture using pen and paper. And for the time being, remember that this is going to be the quantization noise in a typical PCM system. Now, another metric of interest is the mean square value of the output signal. So if M is the number of quantization levels, the mean square value of the output signal is given by S naught is equal to S square into M square upon 3. That we can also derive considering a typical quantization scheme, and M is the number of quantization level. Now another important metric is average signal power, SI, for a PCM system. Suppose that a 0 in a PCM system is represented by a voltage level of 0 volt, and a binary 1 is represented by a voltage level of A volts. So the average signal power is given by SI is equal to A square by 2. Also, if sigma n is the mean square value of noise, then we ensure that A is equal to K into sigma n, where K is a constant. And the value of A is chosen in such a way that it is much larger than the noise. It is deliberately chosen. Otherwise, our system would be of no use. So the noise figure, another important metric is noise figure, and which is nothing but the ratio of SI upon NI with SO upon NO, where SI is the average signal power, and NI is the input noise power, and same thing is at the output signal and noise. So this ratio is known as the noise figure, and it's very one of the most important metric for evaluating a PCM system. Now let's compare the noise uh, relations in PCM with the noise relations in delta modulation. So the metric in delta modulation is also this are also the similar. However, the signals are somewhat different, because if delta t is equal to the difference between the original signal, original message, and the uh, approximated message. So original message, we can say it is mt, and the approximated message is n cap t, and its difference is delta t. We can plot a probability density function. We can find a probability density function corresponding to it, and this is given by f delta is equal to 1 upon 2s, where s is the excursion of that particular quantity delta t. So this delta t, you can also call it quantization error, difference between mt and m cap t. So the maximum quantization error in DM, as long as the slope overload is avoided, is s, and that's why this probability density of quantization error is written in terms of s. So it's a function of s given by 1 upon 2s. Now the normalized power, if we want to calculate it from the quantization error as a function of time, is given by del t square. It's a function of time because it's a probability density function. So we are going to integrate it over minus s to s, and that will give us the probability density, normalized power of that probability density. So normalized power is given by del square f delta t delta, and that comes out to be s square by 3. Very important relation. It can be reasonably assumed that the frequency spectrum of delta t, the quantization error, is wide over the range of, say, a particular value to a particular another value fb, where fb is the reciprocal of the step size or the step duration. So I'm talking about the step duration of the dm, staircase function. Okay, so if it is fb, then the noise power can be given by s square upon 3 into fm upon fb, because the output noise power in the baseband frequency range is assumed from 0 to fm, fm being the upper limit, and fb is the reciprocal of the step size. So the output noise power in dm is given by s square into fm upon 3 into f. Now signal power is dm is what? We have calculated noise power. What is the signal output signal power in dm? It is given by the average value of the message signal, the output signal power. The average value of output signal power is given by a square by 2. But what was the signal? Signal was the sinusoidal signal a sine omega mt. And if we give it a thought that where the maximum slope occurred at the message signal, and what was its limiting value? So the maximum average slope of approximation m cap t is given by s multiplied by reciprocal of the step size. So S into 1 upon tau is equal to S into FB, that is the maximum average slope of the approximating signal. Approximating signal means that staircase function. Therefore, if the bandwidth is omega m into A is S into FB, so we have a value for A in terms of FB and omega m S, and therefore we can calculate output signal power in DM as S naught is equal to S square FB square upon 2 omega m square. So all these relations should be learned by heart before we go on doing some numericals on them, and we also do a proper derivation before everything sinks in. So output signal to quantization noise ratio in DM, just as we had calculated it for PCM, we are going to calculate it for DM also. So this is given by S naught upon NQ, which is the quantization noise, and using the above relations which we have derived earlier, using these two relations here, we can obtain it to be 3 upon 80 cube of FB upon FM. That is output signal to quantization noise ratio in DM. So there was a comparison between the noise performance of PCM and DM in typical settings and typical scenario, and now we are in a position to solve some real world problems which are posed to us in the form of numericals. Thank you.